Hello everyone. Today we're going to be talking about moving beyond white noise for random number generation. There's links in this presentation, so I'll make sure and send out the slides so you guys can see them as well. We'll put a link in the description or something. So before we get into the thick of it, let's start with some teaser images to get a preview of what this is all about. So here is a one sample per pixel stochastic blur, using the blur kernel weights as a probability for which singular pixel to sample. So we're not taking all samples of the blur, we're only taking a single sample within that kernel and using random numbers to choose which of those samples to take. On the left, we use a hash function to generate the random number used for that selection, and so that's just regular old random numbers. And on the right, we use something called blue noise to do the selection instead. So both of these images have the same error, but the one on the right has much higher perceptual image quality, as you can see. And so I really want to stress here, the algorithm to render both of these is the same. It's just the source of random numbers that's different. And that's basically the crux of the entire presentation today. So the same idea is applied here to more traditional types of ray trace rendering. And the core idea is that in randomized rendering algorithms, white noise does work, but you can usually get much higher quality results for the same cost by just changing your source of random numbers. And when I say better results, I'm not talking just about convergence speed, like you hear talked a lot with low discrepancy sequences, but I'm also talking about perceptual error, like you can see in these images. And this is actually something that has come up in games before, like this topic that I'm going to be talking about today. It was first made more mainstream in game dev in 2016 by PlayDead with their game called Inside. They used blue noise specifically for a variety of effects with great success, such as the specular reflection shown here. And so I'm going to be covering like motivation for that, and then I'm also going to be talking about where the state of the art is, which is even coming out in the next week or so. So yeah, very leading edge, I guess you could say. So with the motivation out of the way, here's how the presentation is going to go. It's broken up into 3 sections. We're going to first talk about randomness and fairness, then stochastic rendering, and lastly, we're going to talk about noise textures and error patterns. So first up with randomness and fairness. So there's something called the gambler's fallacy, and we'll go through that. So let's say you flip a coin 3 times and get heads. What are the odds that if you flip the coin again, you'll get heads again? So we all know that a fair coin should give you heads half the time and tails the other half of the time. And we've seen 3 heads come up. So surely the odds are less likely to get heads again, right? So what do you think? A, B, C, or D? The answer is C, right? On this 4th coin flip, it's a 50-50 chance whether you're going to get heads or tails. And so why that is assuming this is a fair coin, the odds of getting heads every time you flip it is 50%. And what it is that each flip of the coin is an independent random number, which means that previous coin flips don't affect future coin flips, right? Each one is independent. It's only as we flip a very large number of coins, or we do a lot of coin flips, that we can expect the number of heads to start matching the number of tails. For smaller numbers of coin flips, there's absolutely no guarantee whatsoever. And so this comes up in video games all the time. And you've probably experienced this yourself. So let's say that killing a boss in a video game gives rewards following the probability table on the right. So I'm going to ask you, how many times will you have to kill the boss to get those epic boots? And so it's a 10% chance, so it should be 10 times, right? However, we know this isn't the case, right? You might get lucky, and it might only take 5 times. Or you might get unlucky, and it could take 20. And so, yeah, what do you think is the answer here? How many times will you personally go have to kill the boss to get the boots? And yeah, it's D, unknown. We can say that on average it'll take 10 boss fights, but we don't actually know how many it will take you personally to do it. Just that if you average up a lot of players, it'll take 10. And so you personally, you might get the boots on the first kill of the boss, or it could take 100 kills. And with every selection from the loot table, it's an independent random number, and so each time it's a 10% chance. It doesn't matter how many times you've passed or failed prior. And so because of this, you hear a lot about players saying that certain games have bad random number generators in them, right? Because they personally have had bad luck, is what you can call it, right? Like they killed the boss 20 times and still the boots have not dropped. And that's just going to happen with some players. However, when game designers understand probability, they realize that the average experience is not the same as any individual player's experience. And so game designers can actually take measures to avoid this problem. And one way to deal with this is to make a list of all the possibilities, all the possible outcomes. And since they were all divisible by 10, we were able to make 10 outcomes. Then we shuffle that list, and when the player kills the boss, you give them the next item in the shuffled list. And so this works well at giving each individual player a more consistent experience, but it comes at the cost of having to store a shuffled list and the player's index into that shuffled list. And so something to kind of help this is we at Seed have an article on how to access items in a shuffle without actually shuffling, and I've included the URL here if you find that interesting. And so doing that, you get rid of the need for storing the shuffled list itself, but you still do need the player's index into that shuffled list, as well as the random seed used for that shuffle. And so yeah, essentially you need to track how many times every player has killed that boss, so that when a specific player kills that boss, you can give them the next item in the list. And if you're going to be resigning yourself to that storing an extra value to help make the player's experience better, there are other methods that you can use to help make it more fair. And so, for instance, a maximal period LCG is one of those things. Also, finite field generators is another term that you can search for. However, shuffling is still random, and so I don't know if you noticed this, but in the shuffled outcomes, the boots dropped on the first run. And so even with a shuffle, you can get lucky or unlucky about where the loot you're trying to get falls within the shuffle. But the nice thing with a shuffle is you definitely are not going to get the boots until this shuffle is over and a new shuffle begins. So there's actually another thing we can do as well. This is one of my favorites for kind of like 1D random number generation that you need to be more fair. And that's if you're allowed to store a single value for this purpose, what you can do is you can store a value between 0 and 1 that you initialize to a random value. And this is the seed for our sequence of random numbers. And then whenever you want the next random number, you add the golden ratio to it, throw away the integer portion to keep it between 0 and 1, or use modulo 1, and you use the result as your next random number. And so here it's like the index into the shuffled list and the seed are the same value, right? You only have one piece of storage instead of two. And so I've shown 30 item rolls below, rolling from the treasure table, with two different seeds for the golden ratio sequence. And at the bottom, I've also shown 30 item rolls with white noise as well. And so within every group of 10 item rolls, if the histogram exactly matches what the loot table says it should be, I've colored that group green. If it's wrong by one item, it's colored yellow. And if it's wrong by more than that, it's colored red. And there's an orange one that I'll talk about in a second. So just looking at the red, green, and yellow, you can see that the golden ratio sequence is pretty good at generating strings of numbers that match the histogram, but it's imperfect. However, it's a lot better than white noise for generating sequences of numbers with the correct histogram for small numbers of samples. And so this means that an individual person's experience will closely match, or more closely match, what the loot table says their experience should be. And so, with this golden ratio sequence, you can count on getting the boots roughly every 10 times you kill the boss. Where with white noise, it's very random, as we've all experienced in video games. And so, the orange section, it's off by more than one, but let's talk about that a little bit. So, the yellow section before the orange section is missing a 3, and that's why it's yellow. But if you look at the orange section, the first value in that section is a 3. And so in a way, it's kind of like restoring the section before it, right? Like the yellow section should have had a 3 in there, but it's right after the yellow section that there's a 3, so it approximately fixes it. And also, the yellow section had too many 2s, and the orange one has too few. And so, in a way, that's another way that the orange section is correcting the yellow section that came before it. And so even though the orange section is off by more than one value, it's sort of restoring the yellow section that came before it, if that makes sense. And so the golden ratio sequence is imperfect, but as you can see, it tends to have great properties for small sample counts. So seeing how well the golden ratio worked, you might be tempted to try other irrational numbers in the same way. And so let's explore that a bit. So here we show the golden ratio sequence on a circle. We take the value that's 0 to 1, and we multiply it by 2 pi to get an angle, and we're showing that angle. So this circle basically represents the values from 0 to 1 as 0 to 360 degrees. So the golden ratio samples the circle pretty well over time, and every new line that is added actually goes into the largest gap that exists, which is a pretty cool property, right? It fills in the space really well. And so seeing how it works here on the circle and how it fills in the largest gaps, this hopefully gives you kind of like some intuition why when we were rolling treasure from killing the boss, that it gave random looking loot rolls, but it gave a flat histogram. Like all the possibilities were well covered. This is kind of like a visual way of showing that. And I'm also showing the continued fraction underneath the label that says golden ratio, and it's the 1 semicolon and then 1, 1, 1, 1. So the continued fraction for the golden ratio is just an infinite string of 1s. And within a continued fraction, wherever you see a large number, that means it's well approximated by some integer division. And so because the golden ratio is just an infinite string of 1s, this is a reason why people consider the golden ratio to be the most irrational number. That is, it's least well approximated by any integer division, with the integers being arbitrary magnitudes. So let's look at another one, another irrational number, and that one is pi. Another popular one. So, pi is kind of like the poster child for irrational numbers, which is funny because if you look at it being used for the same purposes of random number generation, pi just kind of like goes around the circle in order, and it nearly repeats itself every 7 steps. And so this shows that pi is very nearly irrational. And that it nearly repeats every 7 steps speaks to why the fraction 22/7 is such a good approximation for pi. And similarly, 355 divided by 113 is even better. And in the continued fraction, these two correspond to the first, the 15, and the 292, respectively. And then lastly, let's look at the square root of 2. So the continued fraction for the square root of 2 is an infinite string of 2s. So it isn't quite as good as the golden ratio because it's a little bit more well approximated than the golden ratio is at each step of the continued fraction. But it's close, right? Like it's second place to the golden ratio. And you can see as it samples the circle that it does a pretty good job. So like the takeaway that I want to give to you guys here is that not all irrational numbers are the same. And so if you want to use irrational numbers to do like this sort of random number generation, you have to be careful which ones you use to make sure they have the properties you want, which is that they're highly irrational. And as you can see, there's like a limited number of the best irrational numbers that you can use, at least for 1D. In higher dimensions, it gets more complicated. So outside of game dev, but still within graphics, here's another usage case for better random numbers. And so sometimes when we're rendering something, we have some number of objects, and we might not know what that number of objects is in advance. Like it could be 10, could be 100. And we want to give them each a unique color. And we want those colors to be maximally distinct from each other. And so like as concrete examples of this, we might be coloring lines on a line graph, or maybe we have a 3D model visualization tool in an editor, and we want to visualize the material indices on the mesh, each having a different color. And so in both of these situations, we have an index, and we want to turn that index into a color. And so one way to do this is you can just use a hash function where you put in the index and out comes three values for an RGB triple. And so when you're doing that, it's a hash function and it's white noise. So there's nothing making sure that your numbers or your colors, your RGB values are distinct. And so in the results, in the top, the white noise results, you can see, for instance, that the colors for D and E are very similar greens, for example, right? Like there's nothing to prevent that. And so another way to do this is to look at the HSV color space, which is hue, saturation, and value, as shown in this diagram, and see that hue is actually a circle. And so much like we did in the last slides with the golden ratio, we can actually sample that hue circle using the golden ratio sequence. And knowing how the golden ratio works, we know that each new sample we add is going to be in the largest gap between colors that currently exists. And so, yeah, so what's going to happen is that for any number of colors, without knowing how many that is in advance, we're going to end up with that many distinct colors that are like nearly maximally distant from each other around the circle. It won't be as maximally distant as if you knew the number in advance and just evenly divided the circle. But the benefit is you don't need to know how many you have in advance. And so comparing the golden ratio sequence on the bottom to the white noise value on the top, you can see it's just night and day, right? Like the golden ratio sequence colors are much more distinct than the white noise values are. Something important to note, though, is that to do this, you do need your values to be sequential, like from 0 to n. In situations like this, you might find that you have object names, but not indices, and you might think that you can hash them and then put them through the golden ratio sequence to make these colors. But the problem is when you hash the names to get your indices, those indices are white noise. And when you put them through the golden ratio sequence, they are still white noise when they come out. So you're going to get results like the top. So yeah, you need sequential indices for this to work. And so like we've seen over the last couple slides in this section, using irrational numbers to make a pseudo-random sequence is both easy and powerful, but it does have a downside. And that downside is it's deterministic. And so it's not suitable for something like a poker game or similar. And this is because if a player knows that you're using the golden ratio as a random number sequence, they can just look at your values and then know what the next values are going to be that you're going to generate. And so they can predict the future, so to speak. and more so, like they don't even need to know that you're using the golden ratio generator. They could just write down the random numbers that are coming up, and they can see the pattern. Like it's a linear function on a ring, right? Like using modulus. So it'd be pretty easy to guess. However, if we wanted randomness, but we also wanted the property of like good coverage over the entire domain, we can do that. There's a great algorithm called Mitchell's best candidate, and basically, you can generate any number of points that are randomized but roughly evenly spaced. And much like the golden ratio sequence, you don't need to know how many that is in advance. You can just add more points if you need them. And so when we do that, it's called blue noise. And it is randomized, but the points are not completely independent from each other, right? Like I was saying that a coin flip, each one is independent from each other, where a previous coin flip does not affect future coin flips. Well, with blue noise, that isn't the case. Future coin flips are impacted by previous coin flips. So if you had a blue noise coin and you had 3 heads in a row, then the chances are in fact higher that you're gonna get tails next. And so in a way, when people think that random numbers work like the gambler's fallacy, right? Like that we're due for tails. While regular random numbers don't work that way, blue noise does work that way, which is kind of interesting. So higher dimensional blue noise can be useful for placing objects as well. And so if you're looking at these points, they could represent various things, like points of grass on the ground, hair follicles on a head, or they could be, if you have a mesh that you want to make it look like it's on fire, these could be the locations of fire particle systems to make it look like it's burning. So in all those situations, you want the randomness that comes with white noise, like you see in the middle, but you also want like even coverage, like you get with the grid on the left. And so with blue noise, you kind of get the best of both worlds. The points are randomized, but they give pretty even coverage without clumps or large empty voids, and it looks very organic, right? And so it's kind of like a midpoint between these two options. And in fact, nature uses blue noise for photoreceptors in the eyes, which is kind of interesting. Here on the left, we show an article about the eyes of a chicken, the photoreceptors being arranged in a blue noise pattern. And I believe it's actually a multi-class blue noise pattern for the different color receptors, where they're each blue independently as well as combined. And then on the right, we show, some cones in the retina of a monkey. In other fields, you won't hear them use the term blue noise, however. You'll hear them call it disordered hyperuniformity. And so it's disordered because it's randomized, and hyperuniformity because it has even spacing and even coverage at low sample counts, essentially. So that's the end of this first section on randomness and fairness. I only showed 2 usage cases, which was like a treasure table when you kill a boss, and colors for objects. But hopefully you can smell what I'm cooking. This concept, or these concepts, they generalize widely to graphics, game dev, and even just generic algorithms, right? Like anything that uses random sequences. The golden ratio sequence is actually a low discrepancy sequence, just like Halton, Sobol, and friends. And so because of that, those other LDSs can also sometimes work well as RNGs. So that's just something to keep in mind if you need higher dimensional random sequences, I guess. So blue noise can also be a great way to get randomized but roughly evenly values or samples if you want them to be less predictable. And white noise is usually pretty bad unless you really want the statelessness that you can get from it, like no storage space needed. or if you want the maximal unpredictability, like in a gambling game. Okay, so next up, let's tie this into rendering. We're going to be talking about stochastic rendering. So modern rendering is full of integration, and this is mainly due to a fixation on realism. Path tracers generate photorealistic images by solving this recursive integral numerically via ray tracing, and this is called the rendering equation. And so if you've seen in recent years ray tracing take off, the reason why is because it allows us to take individual samples for integrals like this, where rasterization can quickly give you a lot of samples, but you can't choose like which ones you want. Like it's kind of like buying in bulk versus handcrafted stuff. So yeah, real-time rendering has followed movies for a long time, and the rendering equation is no different, right? Like path tracing and stuff first came from movies, and then now in games, we've been trying to kind of emulate that ever since PBR was introduced to game dev. And so much like that, movies are kind of starting to branch out into stylized rendering, and so I think games are going to be following suit. But in those stylized movies, even they are based on proper light transport and solving, the rendering equation. But what they do is they'll use, they'll solve this to get like light bounce and good like GI and whatever else, small scale shadowing. But then they will use that information to drive the stylized process. And so, for instance, where it's darker, maybe there will be thicker cross-hatching. And so because of this, I think games will probably be making a move away from realism in the near future, like movies have, at least some games. But even then, we're not going to be leaving behind integrals anytime soon. So I feel like stochastic rendering is here to stay for a long, long time. And so with real-time rendering, we can't afford to do full path tracing in real time. So we use algorithms to approximate parts of the rendering equation, and we composite them together to get our final frame. And so even those things where we're just dealing with part of the equation at a time, even those are integrals. And so here are some common features of real-time renderers. Like on the left, we have fogs and clouds. We have small-scale shadowing in the middle. And then on the right, we have rough specular reflections. And so like each of these things are integrals, right? And then we composite the results. A nice thing about numerical integration is that you can tune it for quality versus speed. And this is super helpful for real-time rendering in games. And so if you need something to be faster and you're okay with it being a little bit uglier, you can reduce the sample count and you get that. And if you need something to be higher quality and you can afford more computation, you can just increase the sample count and you get that. And so this is great when you're trying to fit your renderer into that 16 millisecond budget, right, to hit 60 frames per second, or 8 milliseconds if you're trying to hit 120. And very few algorithms are this flexible. So they are very appealing in that way. But we can actually take other algorithms and turn them into stochastic sampling problems to gain the benefits. And so like I list 3 of them here on the right. The first is texture sampling. And so if you're doing bilinear texture sampling or, anisotropic, you might be reading quite a few pixels for the blend to happen, right? Like it's eating up your memory bandwidth. And so you can actually make that stochastic where you take one or even just fewer texture samples and blend those. And what that will do is relieve some of your memory bandwidth problems by reading fewer pixels. It makes the result uglier, but if that's the right trade-off for you, it's nice to be able to do that. And once again, you can scale that for quality versus speed, depending on what your specific needs are. And so similarly with convolution, like blur, depth of field, and other filters, you can use the kernel weights as probabilities and just read fewer pixels. And so like we showed that at the beginning of this presentation with the 1 sample per pixel blur. That was the most extreme version. But if you don't need to go that extreme, you could do 2 samples instead of 9, or 2 instead of 25, whatever the case may be. And it'll be a little bit better. And then lastly, there's things like material blending, where if you're trying to render terrain, and the terrain has like nine different materials on it that you have to blend together with different weights, you can actually use those blend weights as probabilities and evaluate a smaller number of those materials and blend them. And so that will help both with your compute and your memory bandwidth costs. And it'll reduce the quality, introduce some noise, but it can alleviate some of those problems. There is another topic here on material blending and similar, where doing this can make some like cache coherency problems, but that's a different topic for a different video. Okay, so let's return to our friends from the last section, which is white noise, blue noise, and the golden ratio low discrepancy sequence. So these graphs, they show the convergence rates of those 3 sequences when used in numerical integration on a few simple functions. And so the key takeaway that you should get from these graphs is that white noise converges the slowest and the golden ratio converges the fastest. Also importantly, blue noise is not really much of a contender for integration. There is something called projective blue noise, which works a little bit better in high dimensions, but in general, for integration speed, you're best off using a low discrepancy sequence. But oftentimes in video games, we only get 1 sample per pixel, or maybe we get that 1 sample per pixel at a reduced resolution, so it's even effectively less than 1 sample per pixel. When you're working in that situation, it doesn't really matter what your convergence speed is, right? Because you only have 1 sample. And we do have TAA, or temporal anti-aliasing, which does leaky integration over time and helps you gather multiple frames for a final result. But even with TAA, you need individual frames to be presentable, because if a large amount of your scene is disoccluded, or your camera teleports to a new location, you really need to have a presentable frame right away. And so the question is, how can we make good renders with such low sample counts, right? Especially when all the literature out there is about low discrepancy sequences and how you can converge faster with subvol and such. What do we do? And so that leads us to our third and final section, which is on noise textures and error patterns. Okay, so stepping back from rendering for a moment, seeing out as the high-level overview of what rendering is, we can see a single pixel rendering that pixel as evaluating a function y equals f of x. And x is whatever inputs you might need to render. And so this is the scene, the pixel position on the screen, the frame number, random numbers, shader constants, all those things. So that's basically our x vector. And y is the RGBA output. It's the final color of the pixel. And so this, looking at rendering as a function, is essentially how a pixel shader works, right? And a GPU is good at running a bunch of these in parallel. The thing about F, though, is that it can be path tracing, as it is in this screenshot, or it can be ambient occlusion, or it can be filling the G buffer, or anything else. And so I mean rendering a pixel in the most general sense. And so within all these possible functions for rendering, we can make some statements. Basically, it's generally true that if we have our x vector full of all that, that state we needed to render a pixel, if we make small changes to it, to any of those parameters, that the output pixel color should also be pretty similar, right? The changes in the output pixel color will be small. So small changes in make for small changes out. And there are some exceptions to this, like geometry edges. If you move past a triangle, right, you're going to have different colors. Sharp reflections are the same way. Like if you move a small amount on one of those spheres, the reflection is going to make the pixel color different. Also shadows, like if you have sharp shadows with a small penumbra, right? Small changes will change the shadowing in a large way. And also just like detail in albedo textures, right? Like if you put a texture on an object, the pixels could be very different that are right next to each other. And another exception to this would be a hash function, which hash functions are designed to have this assumption not be true. A good hash function or random number generator makes it so a small change in internal state causes a large change in output. But we usually are not rendering like TV static or other things that need hashing. So in general, moving a small distance across the pixels or other small changes in X results in having a similar color. Or, similarly, if you're shooting shadow rays, moving that shadow ray a little bit, like the angle, changing the angle a small amount, is going to make only a small difference to the result of the rendering. And so this kind of implies that large changes in X will also make large changes in Y. And that's also somewhat true, but it's limited to the possible values of Y. Like if an object is always in shadow, no matter what direction you shoot a ray in, changing the ray direction isn't going to change your result. But if it's partially in shadow, then wild changes in your ray direction should make kind of wild changes in the answer about whether or not it's shadowed. And so taking those statements more generally, what it is this means that if you have a noise texture, which is like pre-generated random numbers for your rendering, if you use that in screen space as a source of random numbers, the resulting render will tend to preserve the properties of that source noise texture. And so on the left, we have noise that's completely correlated between the pixels. It's not even noise, but just a constant value. And correlated noise is called red noise and would give you a similar result, just kind of like a bit wavier. But I'm just using a constant here. And so you can see that within that rendering for positive correlation, that if you are at any specific pixel and take a small step, you're generally going to have like the same colored pixel. The pixels are correlated in screen space. And then in the middle render, we have uncorrelated white noise. And so what that means is that like the output is uncorrelated. And so if you pick a pixel in the render and you take a small step, it's random whether you have a similar color or not, right? Like they're uncorrelated. Each pixel is an independent random variable, basically. And then on the right, we have anti-correlated blue noise, which makes for anti-correlated results in the output. And so if you take a specific pixel and step to the right or up or down or left, etc., you are basically always going to have a value that is very different than the pixel you started at. So the rendering output is anti-correlated. And so just like looking at these three renderings, they all basically have the same amount of error, but like you can see perceptually, the anti-correlated blue noise gives the best result. And so to give you some intuition for why the blue noise was better, let's think again about the idea of randomness and fairness from the first section. And so this shows the value of small regions of pixels on a number line. And white noise has the usual clumps and voids of values, which means the rendered pixels won't have a very even histogram within the possible results, right? You can see a lot of gaps, and you can see points on top of each other where they're getting the same value twice instead of sampling new spaces. And then on the right, we have blue noise, and it's fairly evenly distributed, which is in contrast to the white noise, which means that small regions of pixels will tend to have more of the possible results in the right proportions. And so essentially, blue noise for small numbers of pixels has a more correct histogram over what the possibilities of the pixels should be. And so that's a really nice property. And it is also true of white noise, but only for large numbers of pixels, right? Like in the average of the screen, you're going to have the right histogram. But for very small regions of pixels, like these 3x3 blocks, you are not, where blue noise does give that to you. And so that's one reason why blue noise renders are better. But another reason has to do with digital signal processing and the frequency domain. And so what this is about is that blue noise only has high frequencies, where white noise has all frequencies. As you can see on the right of the slide, I'm showing the frequency space of white noise, blue noise, and a Gaussian low-pass filter. When you blur the renders, you're doing a low-pass filter, which removes the high frequencies, but leaves the low frequencies, right? It's low pass. So with blue noise, there are no low frequencies. So a low-pass filter removes the noise and leaves the image noiseless. Any blur you do is going to remove the high frequencies of the image, and so you can see the result is blurry. But the nice thing is all the noise is gone, right? Like it's a relatively noiseless image. But when we look at white noise on the left, it's kind of like lumpy oatmeal. And the reason for that is because white noise has high frequencies and low frequencies. So after the low-pass filter, all that's left is the low frequency noise, which is those lumpy blobs. And so, unfortunately, you basically cannot use a simple linear filter, low-pass filter, to remove white noise, because it exists in all frequencies. You can't isolate it away from the image. The only way to get rid of white noise is to blur everything away. And at that point, like, there's nothing left of the image, which is not great. So, kind of like a little tangent is, it's said that your visual system applies a Gaussian filter as part of your visual processing. And to me, that makes sense from the point of view of the central limit theorem, right? Like if you have a bunch of different little filters, they're all going to add up to be Gaussian. And so this kind of could also explain why blue noise is perceptually higher quality, even when it isn't filtered. And so whether we're talking about viewing something raw or even filtered, we haven't talked about denoisers. But what's nice is that it turns out that blue noise is also better for denoisers, even though denoisers are trained to work with white noise. And essentially, what it is with blue noise, it's more correct in small groups of pixels, and the noise can be isolated in frequency space away from the image. And so these are things that are useful to denoisers to be able to give you a better result. And so, yeah, that's why Quake 2 RTX had a lot better results when they were using blue noise instead of white noise, which you can see in their presentation. And so, like I mentioned before, temporal anti-aliasing is ubiquitous in modern renderers, and it's a great way to make a better render by amortizing costs over time, right? Like, that's just the dream for real-time graphics people. And so you can use blue noise every frame and use a different blue noise texture, and you're going to get a great spatial image every frame. But each pixel individually will be white noise over time because your blue noise textures were made independently of each other, right? So the pixels, again, are independent over time. And we know from the rest of this presentation that white noise is not great. So you can actually make a sequence of blue noise textures that are not independent, where each pixel is also blue over time. And we published that in 2022, and it's called spatio-temporal blue noise. And so when you use that to render, it makes each frame be nice blue noise spatially, but it also gives you the benefit of faster convergence, even in the case of only having one sample per pixel. And so, yeah, one sample per pixel can be okay. It's pretty nice. And then beyond blue noise, we've developed a new type of noise called fast noise, which generalizes these concepts to arbitrary filters over space and time. And we're going to be showing this at i3D next month, which is May 2024 if you're viewing this later. But you can download the textures and the texture generator on GitHub already, like it's up and it's public. I'll put a link to it at the end of this presentation. And so this diagram here, what it's showing is that each row is optimized for a different filter. And we're showing the filter on the left in frequency space. And then we're showing the noise and the frequency of each noise to the right of it. And so the different columns are different values stored in the textures. So like scalar noise only has a single scalar value per pixel. Hemisphere noise has, I believe these are cosine weighted hemispherical sample rays per pixel, like you would want for diffuse lighting or other similar things. And then we also have like spherical samples. And so as you can see from these DFTs, the noise is optimized for the filter so that when you use these textures for rendering, your render will also largely keep these frequency properties, which will then help when you are filtering them. And so here is an actual example of that. And this is a 1 sample per pixel ray traced ambient occlusion with a moving camera. It's using a depth-aware box filter on that 1 sample per pixel result. And we're doing temporal reprojection with normal similarity to stop ghosting. So like comparing the current normal to the last frame's normal. And we're using exponential moving average to integrate it over time. And so here you can see like our new noise, our fast noise, it just beats everything. And in fact, fast noise completely eclipses spatiotemporal blue noise because it's able to make spatiotemporal blue noise, make it higher quality, but it's also able to make a lot of different things as well. And so in particular, the noise we're using here, it was optimized for a box filter over space and an exponential moving average over time. And so that's what allows it to look so much nicer, is that it's optimized for this exact filtering setup. So kind of an overview of noise textures. So essentially, noise textures are pre-generated random numbers with whatever specific properties you want. We've been talking about optimizing them for perceptual quality or to be easier to filter. But to use them, you just tile them across the screen and use them as a flipbook over time, like this line of pseudocode shows. And noise textures, they can contain scalars, points, vectors, even important sampled vectors or like rejection sampled vectors or any combination of those things. You can optimize noise textures for different filters spatially and temporally. And so essentially, noise textures are a low effort way to get better renders for the same cost. It's like you use the same algorithm, you just change your source of random numbers. So yeah, that's it. That's the end of the presentation. Just a quick summary is sometimes in game development and other times rendering, there can be such a thing as too random, right? Like your randomness can be too random. And when you encounter this, the golden ratio low discrepancy sequence and the other things we've talked about can help that. And in real-time rendering, we don't have the benefit of convergence like you do with an offline renderer. And so we have a couple of options, though. We can improve perceptual quality and convergence through noise design. And so that would be something like spatiotemporal blue noise. Or we can pair our noise with the filters we are using to make denoising easier. And so that's like our new noise coming out next week, which is the fast noise. But a major takeaway I want to impart on everyone is that wherever you see white noise being used, it's a good indication that you are leaving money on the table. And this is true outside of graphics and game dev. If you see a randomized algorithm that's using white noise, you could very well get better results dropping in the golden ratio sequence or similar. But it depends on the usage case. Here's the link to the fast noise textures and generator. So you can go there and you can download textures we've already generated. Or you can get the utility and run it yourself, generate whatever type of noise you want. And lastly, there's my technical blog. You can go there. I have a bunch of articles on blue noise and stochastic rendering and other things. Thanks so much for watching. I will watch the comments, so if you have any questions, hit me up there. Thanks a lot.